power of restarting everything and reopening it. Maybe it'll work again. You know, the classic, right? All right, so it might work. I don't know. Again, remember, anytime technical difficulties like this come up, you all will never be penalized for it. So just keep that in mind. Today, the clear question stuff isn't worth a part of your grade anyway. So we're already in the clear, but in future cases, you know, I'll do what I need to do to resolve it. It'll be a case-by-case basis. It's one of the joys of technology. This will happen to you too. You will be giving a presentation, and it'll all blow up on you. It's normal. It's the joys of technology, and the beautiful thing is, if it happens to you too, generally it's happened to everyone else around you, and hopefully they'll be lenient. Depends. Some people are mean. So don't be a mean person. Be empathetic. All right, so once this eventually opens, we just went through position, displacement, velocity. The next slide will be talking about the graphs that we kind of already got to look at a little bit, so that's nice. And then we're going to kind of get into acceleration. And at that point, you may think to yourself, man, we've gotten through basically this whole PowerPoint, and you are both yes and no. I have given you all the definitions of the words, but what we'll be spending the bulk of the time doing, which this is what I'm thankful that we have the time for, the equations. So I warned you all at the beginning, we're going to get to a slide where it's literally just going to be like 5 equations. And I will talk through those. We're going to get lots of practice with those. It's going to be great. But the kinematic equations are notoriously intimidating for many students because it's a whole bunch at once. Like, that's just the reality. But trust me, when we get to that point, I'm doing the best I can to soften the blow. Once we get to that point, it's going to be fine. It's going to work out great. You're going to learn them. You're going to find we're going to be using these equations this week and next week for 2D kinematics. So you're going to see them for a while, but they're notoriously intimidating for students. Just be prepared for that. All right, so this is where we ended. As promised, we already kind of talked about this, so I'm not going to spend too much time. I will note one thing here. So remember, I told you all that velocity is the derivative of position with respect to time. That means the opposite is true. So you can take the derivative of a position versus time graph. So if I do dx dt, I end up with a velocity versus time graph. And this is where your calculus knowledge comes in. The opposite of a derivative is an integral. So if you take the integral of velocity with respect to time, you end up back with position, or if you have limits on it, you get displacement. So this is another common theme. You're going to see this a lot where we take the derivative of something and we get something, then the opposite is true. The integral of that new thing is the original. So you're going to use integrals in this class. You're going to use derivatives. Neither is going to be especially challenging. I'm not going to give you all any crazy integrals. You all are in Calc. I think you all have. Do you have to take Calc 2 right now, or is it like a? You may or may not be in Calc 2 right now. You will see unpleasant integrals in Calc 2. Calc 2 is going to teach you that integrals are way worse than derivatives. Derivatives are easy. Derivatives, you can always do a derivative. You just follow the steps. You get the answer. You will find that integrals are the ones that it is very easy for me to give you an integral that is like impossible. If you haven't seen this already, for example, the integral of like cosine to the 3x dx. You will learn about how to solve that in Calc 2 through the joy of trig sub and trig identities, and that one's at least doable. That one's doable. You know what? And here's how easy it is to make this a nightmare. Oh. Boom! Oh my gosh, now it's awful. Oh, no. All this to show you I'm not going to give you integrals like this. No, this is maybe USO. I don't even like.
Integration by part.
The lesson that I mentioned this is that, again, this isn't to do with physics. The lesson here is that integrals are worse than derivatives. Calc 2, Calc 3 is basically going to be doing a bunch of integrals. That's like the career moving forward, is how to do a bunch of different integrals. In this class, I will show you We're going to have examples where you need to calculate the integral because they calculate something. So we're going to calculate work. That's going to be the integral of force with respect to distance. In physics 2, you're going to calculate magnetic fields. It's an integral. There's lots of integrals that calculate real-world quantities. And this is where some of the mathematicians come in, where they've learned new and exciting ways to do integrals. You can always force an integral. So if you do programming, you can always do a Riemann sum, if y'all remember that. You can calculate any integral numerically. Analytically means getting the general solution without numbers in it. Whatever. That's a complete aside that you don't necessarily need to know. All you need to know is I'm not going to give you integrals that require trig sub or trig identities or things that require calc 2. All right. Fantastic. We're past that. Okay, I already mentioned this. So, velocity versus speed. We had position versus, we had distance versus displacement. We have velocity versus speed. Velocity is a vector. It has a direction. Positive means something. Negative means something. Speed is a scalar. There is no negative to speed. You're not going to tell someone I'm going 30 meters, my speed is 30 meters per second. Negative 30 meters per second. That would be velocity because the negative means something. Speed is always a positive, always. Velocity can be positive or negative because positive means to the right, negative means to the left. It actually has a direction to it. If I ask for velocity, I care which way it's going. If I ask for speed, I just want the number with the unit. No left, right, up, down, no angle, no anything like that. And again, it depends on the problem. Sometimes you want to know which way you're going. Sometimes knowing how fast you're going is sufficient. Cop pulls you over, they're not going to say which way were you traveling. They're going to just say how fast were you going. Do you know how fast you're going? If they're asking you do you know which direction you're going, then you really messed up. That's a problem. So, but in this class, we're going to care about direction a lot. Up is way different than down. Right is way different than left. Yeah.
Is the negative? Oh, never mind.
Yeah, sure, but I appreciate you asking about it. Anytime y'all have any questions at any point about things, please let me know. Negative 3 I hat is 3 meters per second in the negative x direction. Those mean the same thing. If you give me either answer on the test, I'm a happy camper.
So does the I hat need like a per second?
No, that's a great point. I didn't put units. Look at me. Chump. Don't be a chump. Meters per second needs to be after that because negative 3 I hat means anything. It could be miles per hour, meters per second, kilometers per second. So look at me. See, even you can see I forgot the units. Yeah.
So how do we know if negative 3I represents like displacement?
So that's where the V in front of it tells you. Yeah, that's a great point. So the question is, how do you know whether negative 3 I hat is velocity, position, all those kind of things? This specific notation tells you two different ways. The meters per second automatically is telling you it's velocity. If you had nothing else, meters per second is always velocity or speed. If it's in a vector notation, it's velocity. If it's not, it's speed. Always. If I ever give you a problem, something's going 3 meters per second, that is velocity. Always. That's the benefit of units. They tell you exactly what you're measuring. If I tell you something's 3 meters away, that's position. If I tell you something has traveled a displacement of 3 meters, I had to put the clarification displacement. So you do have to clarify position versus displacement with words. The other one that tells you it's velocity, and this again might be obvious, but it's good to point out. The V equals also tells you that. So there's two ways in this case. And I will always put the unit. Obviously, I forgot to do it here. That's because I made a mistake. I made a typo. But in general, I have to provide you the units. If I don't put a unit, you cannot technically solve the problem without making assumptions. You would have to assume it's meters per second, which is probably reasonable. But that's a mistake on my end. At any point on a test, a quiz, if you're like, is this supposed to have units? You can ask me. And I will come over and look it over. If you ever think there's a typo on something, just ask me. That includes during tests. I am more than happy to clarify, know that is correct. There is every now and then, there can be typos, and once someone spots it, I'll generally advertise that to everyone. But I do my best to avoid that. But if you ever think there's one, ask me. It never hurts, and I will clarify that for you. You don't have to ask that question in your mind. Did he write this wrong? Is there something missing here? I will come, if you're like, am I missing any information in this problem? I will come over and say yes or no, you're not missing information. I won't tell you what it is, unless again it's a typo, in which case I'll tell everyone what it is. But if it's not a typo, I'll just say, no, it has everything you need, and then it's kind of up to you to figure out what you're missing in that case. So, all right. Okay, particle moves along the x-axis in meters according to the following equation. For position, x of t equals 10t minus 2t squared. What is the instantaneous velocity at t equals 2 seconds and t equals 4 seconds? What is the instantaneous speed at these times? And what is the average velocity between 2 seconds and 4 seconds? Try it out. Yeah, do it to it. Again, work with people around you. Utilize the resources at your disposal. This is one from the problem set. If you're like, man, this is so easy, I don't need to do it. If it's so easy, it won't take you that long. That's kind of my thought process. I mean, it's better to check your work. Otherwise, it's going to be a lot more boring. And hey, doing it now means you don't have to do it at home. So that's also the benefit of doing these in class. These are the problems I need you to be able to do. So we got time now. I can help you now. But it's up to you ultimately. You're not going to lose any points for you're not working on it. And the answers are in the problem set. I'm going to pull those up for you all. Oh my gosh. So apologies, y'all. Obviously you can't see the problem anymore, but I'm going down to copy the answers. Back over to here. There you go. And it kind of gives some hints here. So,
if I just
I was like, I just go and ask for you. Yes, there is some here. There is some in that bucket. I always keep my own markers, honestly. But yeah, definitely I recommend carrying one. If you leave one in here, by next class it would be gone or dead. So, yeah. Yeah. So the reason there's a part D is this problem Part D is find the acceleration. So in the problem on the problem set, that's on there. Since I didn't put it on this slide, but then I didn't realize that.
So it was because I just looked at part of it.
Yeah.
Yeah.
Drew off. Yeah. So part C is in the problem set problem itself. But I'm talking acceleration. So I mixed it on this. So it'll go over. Yeah. That was probably feeling wrong. How many questions? Yeah, what's
Yeah, no, I went on my
calculated the velocity
it's still not I should still be
no, that's a great point. You got Yeah, about 2 seconds, that should be -4. The alternative All right, y'all realize part C is not ideal? Hopefully that makes you feel better. Part C, my apologies. Somehow this typo slipped through last semester. It is -4 meters per second. And we're fairly confident in that because I've had 2 different people confirm it and 2 different things. So my apologies there. Again, if you ever think there's a typo, ask me. I will happily double check it in front of you. My assumption is this would be I taught this exact course, these exact questions. Okay, not the student, but these exact questions last time. So the vast majority there was already a beta course before you all, the kind of the spring course, so they got more typos. Fun fact, all these problems and their solutions, I did not make these problems. These came from OpenStax. And so again, this is just further reinforcement that human beings make mistakes. So in OpenStax, that's the textbooks there. I got the solutions from them and all that kind of stuff. And I got the answers from them, and those were incorrect. So it's one of those you're going to encounter. It will happen to you too. Yeah. Oh my gosh, no, I lied. I doubted myself. All right, this is why you need to work things out. Okay. It is 2. All right. I remember this now. It's all coming back to me. The answer is -2. It wasn't a typo. It was not a typo. Let me show you all. So, we'll work through this, and I'm going to show you all the mistake that got made. That I also in my head just made because it's a really easy mistake to make. So let's talk through this. All right. So hopefully this first part is fairly straightforward. You plug in 2. You get 2. You plug in 4. You get -6. Straightforward. Speed. It's just the absolute value of these. Fairly straightforward there. Part C. There is 2 ways to solve this. 2 ways. And I am going to point out to you all the way that most people probably did and where this mistake came from. So, V average. What a lot of people did, and what I also fell into the trap of making the mistake on, some of this because I was just doing it in my head. If I wrote it out, maybe I would have been less likely to make this. V average, a lot of people did V final minus V initial, and they divided it by time. This formula is not correct. This is not average velocity. We're actually going to find in a slide after this is average acceleration. This is the rate of change of velocity. The rate of change of velocity. The change in velocity divided by the change in time is how much my velocity is changing every second. So, what should we do to get average velocity? This is where we have to take a step back and remember, how do you get the average of any number? How do you get the average of any two numbers? It is V final plus V initial over 2. The average of any two numbers, you add them and you divide by how many there are. So, this was the common mistake. A lot of people, we use the equation, and again, I also fell into this. You're in good company. Vf minus V naught divided by delta t, that is not average velocity. Average velocity, so this is average velocity. Average velocity is xf minus x naught divided by the change in time. This and this are clearly not the same thing. Those two things are not the same thing. So when you kind of see it that way, hopefully it kind of makes it a little bit easier to remember. But it's an easy trap to fall into. And the beautiful thing is, if you made that mistake today, you'll be less likely to make it in the future. We tend to learn from our mistakes. When you touch a hot stove, you tend to not touch the hot stove again. Once you make a mistake, you tend to be less likely to do it. It's one of the ways human brains are wired. All right, so case in point, there's two ways to do this. So you can either calculate the position at 4 seconds and the position at 2 seconds and then divide that by the change in time. Or you add the velocities. And I really want to make certain you all note this. This 2 is not 4 minus 2. I did not get this 2 by doing 4 minus 2. I did this 2 because the average of any two numbers, add them together, divide by how many numbers I added together. If it was 3 numbers, I'd add all 3 of them and divide by 3. Yeah?
Wouldn't that only work with the acceleration?
Yeah, so that's average velocity. Kind of you assume, yeah. You're not getting in. So the question was, doesn't this only work if the velocity is constant? Average velocity, you don't worry about whether it's constant or not. You just kind of, you get the average, and that's not instantaneous. Instantaneous is different than average, and it's a great question. Yeah.
I meant to say since acceleration.
Either way, it wouldn't matter. Yeah, either way, it wouldn't matter. Average doesn't care how the velocity is changing. You can take the average of anything. It won't tell you at the exact time what it is. It'll tell you the average across the times. Yeah. So in this case, this graph, 10t minus 2t squared. I'm not going to pretend like I'm going to draw an accurate graph here, because I'm not. I have no idea what this graph looks like. So let's just pretend it looks all crazy. It does not look like that. It does not look like that. It's some upside down type thing like that. We are finding the average slope between this point and this point. It is not the instantaneous slope, it is the average. It is not the slope at 2 seconds, it is not the slope at 4 seconds, it is the average between those two. Anyway, great problem. I highly recommend a day or two from now, you all go back to this problem and try part C again to see if you make the same mistake. Take you 5 seconds. But that's how you know whether or not you're going to make the mistake on the test or not. You just try this one again real quick and see if you remembered how to do it. All right. Cool. Okay. We're going to talk about acceleration. See if you all can guess what question I'm going to ask. All right. What's the acceleration of Demo Duck right now? The net acceleration. We'll even put the word net acceleration. I have not told you all what the word acceleration means, so use your background knowledge, see what you all come up with. What is the acceleration of Demo Duck right now? There he is. He's still sitting here. He's having a great time. Look at that smile. What do you think, Carlos? Right. 0-1. That's fine. I haven't touched all the units yet. Does anyone know the units? You'll see that. I haven't taught you that, obviously. But it's an interesting exercise. The challenge here as well is, remember, you got to try to figure out the units.
If I cover this distance in 2 seconds, I would probably less than an hour. If my velocity changes from here and go faster from here, then I'm accelerating.
Yep, and that was the other one. Yeah. So x7 minus x sine divided by
Yeah, he did acceleration faster than
the bottom one. Yeah, so I would, for, if you add the velocities, that's right. I was referring to this one, not that. You can use that. Both work. Yep.
But this would be final minus
Yep.
initial.
Position. Yeah, so x is position. So final position minus initial position. Where you have to calculate it. You haven't calculated it yet. Nope. So you calculated the velocity initial, just for your For part C, you can just add those divided by 2, or you can calculate the final position by plugging in
well, I guess like
2 seconds.
But yeah, it is weird just like
plugging 4
here's time.
seconds.
Yeah. But if you say per second.
Here, I don't need the derivative.
You have to get position, you don't need the velocity, you get velocity. Yeah, if you take the derivative, it becomes a function of velocity. If you leave it as is, it's position. If I give it to you as a position, yeah, that's x. All right, what y'all got? What y'all got? What are y'all thinking? 0 meters per second per second. Ooh, I like the way you actually worded that. All right, nice. Any other thoughts? Yeah. Oh, there you go. All right. So again, reference frame. I've told you all that is also a valid answer. I have no idea if the number is accurate with reference to the sun, but let's just say it is. Yes, there is an infinite number of correct answers here depending on your reference frame. The nice piece here was reminding us units matter. And I love that you all actually mentioned, so I love that people said meters per second per second. No, you're not going to write it like this. So I'm going to show you on the next slide that these two things are the same. Meters per second squared. But this gives you an understanding where this comes from. You all might have taken a physics class in the past and seen meters per second squared, and you're just like, it is what it is. But it's like, what's up with the second square on the bottom? The logic is position is meters. The unit for position is meters. If we then take the derivative with respect to time, we get meters per second because we divided by time. If we then, and that's velocity. If we then take the derivative of velocity with respect to time, we're going to do meters per second. 2 seconds on the bottom, second squared, ta-da, you've derived the units for acceleration. The units for acceleration are meters per second squared, and it's just derivatives all the way down. So acceleration is how much your velocity changes with time. Velocity is how much your position changes with time. Position is position. It's A, that's nice. It's a vector, it's got a direction. It matters which way you're accelerating. And this one gets a little trickier in some ways. A positive acceleration does not mean you're moving to the right. That's something I really want to, I'll just mention now. A positive acceleration does not mean you're moving to the right. We'll see some examples of that. It is the derivative of velocity with respect to time. This can also be written, it is the second derivative of position with respect to time. These are the same thing. Derivatives all the way down. If I give you an equation for acceleration, you can integrate it twice to get back to position, or once to get to velocity. And look at that. We see at the bottom that equation that we used previously. It is not average velocity. It is the average acceleration. Vf minus v naught divided by t. So that is where we get to see that again. Remind ourselves. Yeah.
I think it's dt, like with the
Oh, a second squared. Yeah. We do have to do the second. Thank you. Yep. Second derivative, that also gets a 2 on the bottom. So both are correct. Acceleration is the derivative with respect to velocity. The derivative of velocity with respect to time. Acceleration is also the second derivative of position with respect to time. So to just clarify. X dx dt dx dt, that's velocity, that's acceleration. So you can go from one to the other. Put little hats on it, or little vectors on them. So, derivatives, they're useful. You all learned, this is why you have to take calculus before this class. Calculus is a tool, and it lets you solve new things and discover new things. It's like algebra, just another tool that lets you do things. Without calculus, we cannot get the instantaneous velocity. And we're going to find all sorts of cases in physics, and this is why you'll have to take those classes. All right. And then again, yeah, average VF minus V naught divided by T. All right, so let's see if a clicker works. An object starts at rest and accelerates to 12 meters per second in 4 seconds. What is the acceleration? This is where you got to be careful of your units. Do not mix up velocity and acceleration. That's the big thing I'm going to try to hammer into your all's head over the next 2 weeks. Velocity and acceleration are not the same thing. Use the units to tell you what is what. Yeah, what's up? Yes, great question. This is the average acceleration. What is the average acceleration? Let me add that wording there to clarify that. All right, looking good, everyone. I'll give you all like 4 seconds, I think. 5, 4, 3, 2, 1. All right, so I've gone around and asked a couple people a whole string of questions. So, what'd you get back there? I know you got the right answer. 3 meters per second squared, and that is the right answer. And so then the question to anyone, what's given in this problem? What variables are given? Let's, make sure, because you had to decide this, whether or not you realize it or not, you did do this. We have both the initial velocity and the final velocity. That's really important. So what's my initial velocity? That's a harder one. 0. The initial velocity is 0 because it is at rest. This is very important that you realize There is no equation that just says acceleration is velocity divided by time. It doesn't exist. There is an equation that says average velocity is final minus initial divided by time. You need both. If I just told you an object is traveling at 12 meters per second and travels for 4 seconds, what is its acceleration? You know what? I'm going to give you one just like that right after this, actually. I'm going to purposely word it. It will be possible to solve. But let's see what you all think. All right, so we're going to kind of test that. This is my final. And, you know, this is my time. 12 minus 0 divided by 4. Spot on. So you get 12 minus 0 divided by 4. And we get that 3 meters per second squared. And that's our final answer. Okay. Now, I just told you I'm going to give you one like this, and I am. And we're going to see how this goes. And this will kind of be the test of, does this make sense? This is how I'm going to determine it. Let's see. You know what? I will be able to use the same. So I'm going to basically take the same problem and slightly modify it. So let's reword this. An object travels at a constant velocity of 12 meters per second for 4 seconds. What is the average acceleration? So this will see whether or not, again, don't mix up velocity and acceleration.
What is this? Wait, I can. Yeah.
What is your secret? Okay. What you Looks like D. How do?
Yeah, so the slope is the change.
Definitely. Very nice, very nice.
So it's
All right, we'll go for like 10 more seconds. We'll close this out in 5, 4, 3, 2, 1. Boom, done. Get out of here. All right. What's the answer over there? People I talked to first whose names I don't know. Either one, yeah.
0.
0. Why?
Because it says constant, and constant means there's no change, and if there's no change, no acceleration.
There we go. This is one of the things. So there's 2 ways to do this. You can do this mathematically. You could realize if it's moving at a constant velocity, the initial velocity is 12 meters per second. The final velocity is 12 meters per second. Constant means it doesn't change. So therefore the initial is the same as the final. You can do the, t is 4 seconds. You can do the exact same math that we did in the last problem. VF minus V naught divided by T, 12 minus 12 is going to be 0. Great. So you can do the math. You can also recognize if you ever see the word constant velocity in a problem, you can immediately just say that it's an acceleration of 0. That is like a given at that point. Just like when I say something's at rest, its velocity is 0. If you see the words constant velocity, its acceleration is 0. This is one of those things, the more you do this, the more you'll kind of spot this. But this is a really important thing. Just because something is moving doesn't mean it's accelerating. I really want to hammer that into y'all's heads. Just because something is moving, it's not accelerating. If you are in your car and you're going 120 miles per hour and you're on cruise control so it's set, you are not accelerating. Doesn't matter how fast you're going, if you're going that same velocity, that same speed, you are not accelerating. Doesn't matter how fast, because those are 2 different things. All right. because acceleration is the rate of change of velocity. Okay, now a graph one. Here is a velocity versus time graph. And my question to you all is, what is the acceleration at t equals 10 seconds? So translating it, the definition of acceleration, which is the rate of change of velocity. What does that mean when it comes to a graph? See what y'all come up with. I'm always paranoid with these things. The answer should be
Right. But
we're looking for. What y'all think?
I got
This is, do you remember? Yeah, so acceleration is the rate of change of velocity, which is rate of change of anything slow. Then just calculate. Yeah, and that's yeah, it's easy to get. Someone will make that mistake. Not today, tomorrow. Yeah, it will happen. Give your rush down. Okay.
No, I was looking at the.
Oh, so you okay, so you found at that point you decide your initial is 0, and you got another 0. And so that's where, so everywhere on that line, anywhere on that first chunk, it'll be the same everywhere. It ends up being yeah. If you choose the initial 0, yeah. All right, I think we're looking pretty good here, so I'll close this out in 5, 4, 3, 2, 1. Ka-chow. All right. Who feels confident? Let's do it. What you got?
I got D 0.3 meters per second, because that's the slope at 10 seconds.
Perfect. So there's two ways. It is acceleration is the rate of change of velocity, i.e. the slope. Rate of change of something will give you the slope on that line. Now, there is actually, so I guess technically an infinite number of ways you can calculate this. You all just have to calculate the slope of this line. You can choose any 2 points on that line to find the slope. You could find the slope between these 2 points, which I don't recommend, or these 2 points, this point and this point. It doesn't matter. So some people did, so acceleration average, they did that the velocity was 3 seconds minus 0, final minus initial, divided by the time here, which is 10. Great, that gets them the answer. Other people did the slope between these 2 points, down here and down here, in which case is 6 minus 0 divided by 20. They get you the same answer because it's a straight line. So again, just continue to show you all, there's many cases, many problems where you have multiple ways of doing it. The beautiful thing with math and science, the reason I am in this field, that I enjoy it. This is the way my brain works. It's logical, and logic means if this, then this. Like always. That is our understanding of reality, is that if I drop something, it falls towards the earth, and that should not change anytime. If it does change, we have to figure out why. If this, then this. And now 2 plus 2 is always going to be 4. There is always a right answer, and as long as you're following correct logic, you will get to that answer. It doesn't mean that there's one way to do it. It just means you need to follow correct logic. Whereas in art and things like that, those are great classes. Art is very important, but it's subjective, and it's much harder for me to get the right answer. I don't know. There's not a right answer. I don't do as well in those courses. I took AP Lit in high school. Could not understand the references or metaphors for the life of me. People's brains work differently. That is not to say it is less valuable. It is just to say I am worse at it. All right. So there you go. It's a slope. We kind of went through that. An integral works your way backwards, and it's a good time. Okay. Sure. Do I want to... Okay. This is the problem I already gave you all. It's just got part D tacked on. What's the acceleration at these times? So what's the acceleration at 2 seconds? What's the acceleration at 4 seconds? You do not need to do parts A, B, and C again. You already did those. Part D here is asking, what is the particle's acceleration at t equals 2 seconds and t equals 4 seconds? What is the acceleration at those times? That's the only thing you need to solve here. Try it out, and then I'm going to hit you all with a bunch of equations in one go. And next class, we'll spend time practicing. So. I've given you all a lot today, so we'll probably be done pretty soon, because I'm feeling it in my brain, which means you very likely are feeling it in your brain. We'll do this. I'll show you all the equations. We'll talk through them. Maybe apply them. We'll see. We might wait till next class to apply. We'll apply that. Function for acceleration, you can find it for any time. And I'm asking for instantaneous acceleration. Instantaneous. Not average, though ironically average will get you the same answer. What are we doing over here, y'all? Did you get it? What's the thought process? How can we get acceleration from a position? You take the derivative of once of that function, you get velocity. You take the derivative again, you get acceleration. And then you just plug in the times. Yeah? That's fine. Welcome to the club. We all make the key is just to make the mistakes at times when the risk is that's how we practice it now. There's no risk in missing these. All right, so I went around. How do you get the acceleration? Who's got the recipe? Yeah. There you go. You find the equation for velocity and you take the derivative of that. So we have our position equation, which is 10t minus 2t squared. If we want to get our velocity equation, we're going to take the derivative of that, which will be 10 minus 4t. And if we want our acceleration equation, we'll take the derivative of that, i.e. the second derivative of position. And really interesting, there's no time dependence. So what's my acceleration at 5 seconds? Negative 4 meters per second squared. What's my acceleration at 0 seconds? Negative 4 meters per second squared. At all times now until the end of the universe, if this problem continues, it will experience an acceleration of negative 4 meters per second squared. Now, I will tell you all, something cannot accelerate forever. We will eventually learn at some point in this class there is a speed limit to the universe. Speed of light is the speed limit. You cannot, if you accelerated forever, you would reach infinite velocity, which is not possible. So that is interesting. So this function actually is not true of all times forever, because it would actually break the rules of physics to go faster than the speed of light. Complete aside, I am obviously not going to ask you, what is the velocity at 5 billion seconds from now, because the answer would be impossible. Fun things to think about though, fun asides. All right, I have warned you, I have prepared you. Here's a bunch of equations. All right, here they are. They do not, unless you've seen these before, they're not going to look pleasant. Maybe they do. Maybe they look great to you. Maybe you love these. Maybe you're like, this is fine. I love this. The reality is this is notoriously one of those things where it's like, oh my gosh, look at all these equations. What do I even do with all this? I will teach you. I will teach you. For now, I just want us to look at these equations, and we're going to spend some time talking about where they came from. And then next class, we're going to spend the whole next class is just practicing utilizing these. Because always the question is, how do I know which equation to use? That is always the question. And the answer is, what's given? What are you solving for? Find the equation that has what you have and what you need. That's generally what it falls into. So, I'll give you all some time to jot these down. We are then going to talk through these. Didn't just come out of, these weren't written on a wall somewhere and someone found them and gave them to us. Like, we had to develop these. There is logic to where these came from, and the logic is logic I've taught you today. You can probably even kind of think through these yourself if you want. Some of these you have seen. But we'll get there. So I'm going to go a few more seconds to kind of jot this down, and then we'll start talking through them bit by bit. But yes, you will want these in writing somewhere. I have a formula sheet that's online. You will have these on the test. Eventually you will have these memorized, not because you have to, but because you will have used them so many times. So, now the next 2 weeks is basically just using these equations. Next week we'll also introduce an extra dimension, but it'll be fine. Okay, so let's start kind of talking through some of these equations, just to, because if you can understand where they come from, they're not as scary. If you understand where they came from, even if you forget them, you can kind of make them yourself. Every single person in this room has a skill set to understand where these equations came from. If you don't understand where they came from, you can still use them. But it will make your life easier. It will make you feel more comfortable with them. It'll let you check your mistakes, all that kind of stuff. It's one of those, if you conceptually understand something, you're less likely to make a mistake on it. So we're going to start in order. This first one, something I want to point out, this VT is just final velocity. It is the velocity at some time, at some later time. So we say the velocity at some later time is the velocity I start with plus how much did my speed increase or decrease. Acceleration times time is just how much my velocity increase or decrease. That's all this second term means. Let's just pick an easy example. Say your acceleration is 3 meters per second squared. After 3 seconds, what happens to my velocity? After 3 seconds, my velocity has gone up by 9 meters per second. Every second, it went up by 3. So after 3 seconds, it went up by 9. So you take your initial, what did I start with, and you add how much it changed by. That's where the first equation comes from. What did I start with? How much did I change by? Add those together. Ta-da! That's where the first equation came from. It's just from kind of what the words mean. The next one we've already introduced. If you have two numbers and you want the average, add them together and divide by 2. So we've seen the second one. The third one is basically the same logic as the first one. So this one down here, if you want the final position, take what did I start at, what's my initial position, where did I start, and how much did my position change? If I'm traveling 3 meters per second, literally think what that word means. 3 meters every second. Every second I'm traveling 3 meters. So let's do the kind of the same thing. If I travel for 3 seconds, I have traveled 9 meters. Pick what you started at. So if you started at 5 meters and you traveled an additional 9 meters, I am now at 14 meters. So if we kind of take this and move it over here, and I just made up numbers, if I started at 5 meters, I have now traveled 9 meters. My new location is 14 meters. So equation 1 and equation 3 are the same logic. What did I start with? How much did I change by? Add them together. All right. This one here is one of the crazier looking ones, and you're like, where did that come from? I'm going to have you all derive it. It's really simple. Remember, position is the derivative of velocity with respect to time. Position is the derivative of velocity with respect to time. What's the opposite of a derivative? An integral. So what I want you all to do is position is going to be the integral. Oh my goodness. Silly. There we go. I wrote it wrong. Velocity is the derivative of position with respect to time. My apologies. So if you want to get position, it's the opposite. If I want to go back, so velocity is position with respect to time. So position is the integral of velocity with respect to time. The velocity function is the first one. This is this. Try it out. Take the integral of that first function, y'all. Integrate b naught plus at with respect to time. Try it out. Jot it down to paper real quick. It'll help you be more. Because that 1/2 at squared, so this is the benefit of calculus. If this is an algebra-based course, I just have to say it is what it is. But you all can find it for yourself. See if y'all can get it. I'll go around and help, but I'll give y'all 30 seconds. You're just taking the first function and you're integrating it with respect to time. You are integrating b naught plus at with respect to time. B naught is a constant, a is a constant. How are we feeling? Got it. How are y'all feeling? Exactly. And that comes from boundary conditions. So the way you figure out your constant, you put at t equals 0, where t is all thrown away. And so what's my position at t equals 0? Which is that position. So you're taking this function and you're integrating it with respect to time. So you're doing the integral of b naught plus at. B naught is a number. Just pretend like it's any number. A is any number. So yeah, you're integrating b naught plus at with no numbers. No numbers. No numbers. I made up numbers. Yeah, you're just integrating b naught plus at. So to clarify, give you all kind of a checkpoint in case you're confused. You are integrating v naught plus at. V naught is just a number. It's a constant. A is just it's a constant. So when you're integrating it, treat it like a constant. If you want, make up a number for it. Make v naught 5. Make a 3. If you want it, that makes it easier for you, make up numbers. Yeah.
Would it be helpful if I don't want to give them like cheat for class, but like if we do problems, maybe like I could write these kinematics on the board somewhere,
Yeah?
like before class.
Oh, sure, yeah, that'd be great.
Okay.
Yeah, that way, I mean, if they don't have it in their paper, that'll be super helpful.
Yeah.
All right, so integral of a constant. What happens when you integrate a constant? What goes next to it? The variable. So we put a t next to it because the integral of a constant, you just reintroduce the variable. So the integral with respect to dt is time. You just put a t. What's the integral of a? So a constant times your variable. At. What's the integral of that? 1/2 at squared. And then the question is, we didn't have it. This wasn't a definite integral. It has a constant plus a constant. And so the question is, how do we figure out that constant? Anytime you are doing an integral, to find the constant, you need to know some value. You need to know some value at some point. We know a value at a certain point. Yeah.
Shouldn't it be initial position, like x?
So C, it will end up being initial position, but the logic, how do we know that C is that? What is our position? Yeah.
I mean, like, shouldn't it be x instead of b?
So not yet. We don't have the x yet. We don't have x in this equation, so when we integrate, we can't just pop in an x. So how do we get that x though? How do we get that x is the question. We know a condition. Does anyone know what condition we know?
Well, I thought that was because like plus c is like the y-intercept and the y on the graph is x.
Yeah, so that's one way to think about it. The plus c will be the y-intercept, which is located at t equals 0. At t equals 0, if I plug in t equals 0, this term goes away, this term goes away, and literally think about it. Where am I located at t equals 0? I'm located at my initial position. That is the definition of initial position. Where am I located at t equals 0? So we actually, again, thinking through the physics, thinking through the logic, the result of this is we get the equation that we had over there on the side, plus x naught. Again, these equations don't just come out of nowhere. They come from logic that you all know. And if it doesn't make sense, that's okay. You're not going to be penalized, but if it does make sense, your life will be a little bit easier when solving these things. All right, the last one is gross. The last one comes from algebra. Like, we're not going to spend the time deriving the last one, but I have a beautiful derivation here that you are welcome to look through. It is a whole process. So the first ones are really straightforward to show. And so we did this one. We did this one. Great, those are covered. The last one. Acceleration is the derivative of velocity with respect to time. Then you rearrange it. Then you use the x of t equals x naught. So this is one of those, feel free to look through. This one's not as entertaining. It's just a bunch of algebra. It's a bunch of algebra to kind of take this, plug it into here, and you'll get this kind of thing. So feel free to look at this in your own time. It doesn't give you much conceptual benefit. It's just one of those, again, these aren't from nowhere. And this is a common theme where we can take another equation, plug them into each other, and make a new equation. And that's what we did here. Okay? So I'm not going to worry about it, but feel free to look at it if you want to in your own time. And yeah, at this point, we have introduced the equations. We have introduced enough things for today that I think if I keep going, at some point diminishing returns. Yeah, real quick question. Yeah. It is, this last equation is if you know the initial velocity, you know the acceleration, you know the position, you can find the final velocity. At the end of the day, all these equations are if you know certain things, you can calculate the one that's missing. So yeah, on Thursday, we're going to practice these. We're going to do a lab in groups of 3. Make certain you know who your group members are. You will assign yourself to them during the class. I will make that happen. And make certain you're here because this is our first graded lab. So be here, and I'm around for the next 20 minutes. If you all want to work on anything extra, if you have questions, comments, concerns, I will stick around to the end of class.
There is a mistake in the second because then you move to the other side.
Catch. Whoop. Good catch as always.